Okay, thank you very much for the introduction, and thank you very much to the invitation to this fantastic conference. Actually, this is first time for me to come to Kobe, and this morning I looked at this, the city, entire city, from 30th floor, and that was magnificent. And well, it's completely different view that we have. This is a view from our cafeteria, and we very much like this view. And everyone in here is welcome to come to OIST anytime. Today, I'd like to talk about the quantum machine learning and quantum dynamics. What is the relation between them? And this is a little bit more conceptual talk than probably usual physics or computer science talk. We'd like to see some new directions in the quantum computation development. And to do this, we may need to think about different regime of quantum dynamics and quantum computational processes. So this work I'm presenting here is not only my own work, but it's the teamwork. It's involving many people. And thanks to these people, it's already some of them already left my group, and also the external collaborators. So as we have seen, this is not only, of course, it's not only the superconducting qubits, and recently we have seen other type of platforms coming quite advanced. So neutral atoms and optics probably is there are more to it, but just to make it simple, I just plotted from the beginning of IBM-Q, which was 5 qubits, to the biggest one is 433 qubits. Along this way, of course, we have seen 2019 Google's 54-qubit machine or 60-qubit machine from China, and it is getting larger and larger. However, there is a huge gap still between this type of so-called NISQ processors and fault-tolerant quantum computation. And both ways, but mostly hardware side is a huge difference between NISQ processors and fault-tolerant quantum computers. And because of this gap, the development is not continuous. It's not we are going to add more and more qubits, but we need to have new technology to overcome these scalability problems. Another huge direction or huge effort we have seen is to see how we can use these small-scale quantum computers. So physical qubit is not like a logical qubit, which is noisy, but somehow we may be able to use it for something. Mainly people think about speed up issues, which is sort of hopefully gaining exponential speed up in quantum computation, but we need to start to think it is not only the speed up we should expect from quantum computers or quantum processors. And if we look at 50 qubits, then if we think about that network realized on, if of course it is virtual, but network realized on the Hilbert space is given by the 50 qubits, then we have seen that huge network, which is almost, in terms of the number of nodes, is as big as human brain, so to say. So if we can facilitate this kind of physical systems to do something, and that might be something useful, maybe it's not the way we think as a computation. However, that is another way to exploit quantum system for our technology. And so far, up to sort of some 100 qubits, realizing the quantum system as a computational system and thinking about a fault-tolerant quantum computer as a shared path. But I will see that this is we are at the point of dividing this path to one is to develop fault-tolerant quantum computer. This is very specific technology development, and it is different from other type of quantum technologies, quantum sensing, imaging or quantum communications, quantum crypto, quantum security, all these different type of quantum technologies. But the photon quantum computer, it's really specific technology, and that's sort of going one way, and sort of more different type of quantum compute. It's not maybe not quantum, I'm not quite sure that calling it quantum computer is appropriate, but quantum computational processes taking another route and going to develop practical small-scale quantum computer. And here, so what kind of expectation we should have if it's not speed? Well, of course, we can have a speed up, but also maybe we can reduce significantly the resource. We run the same computation with the same accuracy, or could be much smaller, much lighter, much low energy, and much more efficient technology for computation. So we need to diversify the benefit or advantage a quantum computer would give us. And in this talk, I like to focus on what kind of complexity does quantum computation process generate and how we use it. In here, I'm not talking about complexity class of problems like we talk and well-defined in computer science, but the more sort of physicist way talking about complexity, so it's not well-defined in a sense, but somehow we know some system is simple, like periodic rotation motion is simple, but some chaotic motion is complex. So in that kind of sense of complexity. So going back a little bit back to just to have a 12 qubits. So 12 qubits is very small system compared to the quantum computer available today. But still we can do something interesting. So here we have half side is, well, just first of all, we have one-dimensional chain of superconducting qubits, not necessarily working as a qubit regime because we still have bosonic representation, as you can see from the Hamiltonian. We are using bosonic operators. That means before we define qubits, its still representation is bosonic motion. And we have only 12 of them, and it has only nearest neighbor coupling. That means it's not universal as a quantum computer, but it can do something interesting. So here we have sort of time repetitive control sequence. So it is periodically driven. And if we do this, usually this kind of system is localized if we don't do anything. But because of the driving force, the periodic driving force, we can turn that system into ergodic system. And what happens if we have the connection in between the localized region and ergodic region, then how we can see it. So this is just a background how we treat this kind of system. We usually use Floquet theory. So Floquet operators will give us some very convenient mathematical tool to deal with this kind of periodic driven system. And we extract from the unitary operation, we extract effective Hamiltonian, which is different from the Hamiltonian that physical system originally have because of this Floquet theory. So to see this effective Hamiltonian, so effectively this motion is behaving like effective Hamiltonian would give. So that means it is not really, physically we're not implementing the Hamiltonian, but we create. So that means, so in a sense, it's programmable. So we are programming effective Hamiltonian in a sense. But of course, it is only realizable at a certain time, so it's a discretized system in a sense. And Hamiltonian, we have seen this top square. This is, we're just representing the Hamiltonian in a matrix form. And we just put in colors where the entry number is bigger. So we can look at it this way, but then we can think about this as a network as well. So given this, even no longer the operator, but given this matrix, we can think about what kind of network is corresponding to this network, then we can sort of see how these are connected to each other. So the states are connected to each other. How when a sort of transformation of the state will happen can be seen by our network. In this case, we are using power correlation rule and show what kind of network property we can see. And as we can see, that if we driven hard, the ergodic nature will leak out to localized parts. So then ergodicity will sort of dictate the whole system. That is a left-hand side, and the right-hand side of the figure, B, C, and B4, is still one side is more or less ergodic, but the other side stays as localized. And then we can see a much more complex network or non-trivial network will come out from that kind of dynamics. And if we can use this kind of network to design quantum computation system, that is another way of designing quantum computation. And here is one example of doing it, to use this system to create program. As I said, we can now program effective Hamiltonian. If we do this, then we can run adiabatic quantum computation in the discretized time and to go through, so not changing the physical system, but we can sort of implement arbitrary Hamiltonian to run on discretized adiabatic process. So this is adiabatic quantum computation. Of course, this is rather difficult to implement in time-wise. Of course, in physical sense, it's easy to do this because Hamiltonian we need to implement is much, much simpler than we need to do. However, the time-wise, we need to keep it longer. So in this sense, we need more control over it. So it is rather difficult to do. But mathematically, it is a new tool to investigate quantum systems. And we can find a way to actually implement this kind of computation in a real system. So this is a virtual network because it doesn't really exist as a network like a physical connection of nodes, but still we have some network structure between state. And using this, we will see how it develops first because we want to use it, but we want to know how it develops. And we picked time crystal to see it. And here is, we have again, this is a kind of Fourier system because we have 3 unitary operations. Single qubit operation is H1, 2-qubit operation H2, and the H3, the single qubit, is called disorder. And there are 3 steps, then we just repeat it. And if we do this perfectly, then that means this epsilon in H1 is 0, then we can have time crystal. Usually time crystal cannot be, well, not usually, it's proven time crystal cannot be realized with 2-body Hamiltonian, but we have here only 2-body Hamiltonian. But it is possible because we are looking at a discretized time crystal and we exploit it. And if we change this epsilon in some parameter, non-zero parameter, then we started to see some interesting feature. And that I will show it probably, hopefully I can show it in here. So turn the epsilon non-zero to make it bigger and bigger. Then network gets more complicated. So this is the way we show that the movement doesn't mean anything, only the shape of the network. And if we stop that at epsilon around 0.012, then we can have the scale-free network on the Hilbert space. And if we turn that's a bit more like 0.1, and then we can see the random network. So then we can see that the distribution of the weight distribution will be different. So this means that the reason of we are getting scale-free network is because we have preferential attachment in the system. So we develop this kind of scale-free network. And well, we probably want to use this kind of network to actually do something. So now we try to sort of utilize this complex network into quantum machine learning. And this is that another video, if it moves. So this is how that's kind of this system developed in the networks. And that means in the computation, we have to wait a certain time, of course, and that will be the time of the computation for the quantum part. And we set that time to be able to, the state to have enough complexity, and then we measure it. So here we have input layer, and we start with the input state, and develop certain time. We are not really controlling like programmable quantum computer, but we just wait certain time, as we have seen, of the development of the complexity, and we measure it out on the computational basis. That means we only have a 0 or 1 for each qubit as a result of the measurement. And we put that information into the classical one-layer network and get the output at the end. So this is a sort of, roughly speaking, the model of the quantum and classical combined machine learning model. So the thing it's behind is, maybe it's easy to think this way. So we have input and output and hidden layers in the classical network, and we are replacing some certain part by a quantum virtual network. And think about that can be really a quantum computational resource or not. Because so far we have seen a lot of VQE or variational quantum eigensolvers or quantum kernel methods, or quantum reservoir computation. There are many of the attempts to do this, but it's not necessarily we're seeing the clear benefit out of it. Of course, there are some huge resources used, like using error mitigation. Then we can see the non-trivial result coming out recently. But so anyway, it is not so clear how small quantum system can do something really useful in a non-trivial way. So this is something like quantum version, like extreme learning machine, but the extreme learning machine cannot be converted to a quantum in a trivial way. Then, in a sense, we are using that quantum system as a reservoir. It's not really a reservoir computation as such, but because we are not looking at temporal data, for instance, but it is, we are not really touching it, like treating it as a reservoir. We are not, if once control, the system is set, we are not doing anything else. So in that sense, it is kind of quantum dynamics is working as a reservoir and still is doing some computation. So we called it, this model, we called quantum extreme reservoir computation, even though it is not really a reservoir computation, but it is reservoir computation because we're using quantum dynamics as a reservoir, as if it is a reservoir. And but we have to say we cannot evaluate with the memory capacity because it is not really losing any memory throughout the computation on purpose. And so quantum reservoir provide a large, here it's sort of recalled that quantum dynamics is quantum reservoir. The quantum reservoir provides a large virtual network, and we are using that for the computation. And we only optimize the classical part. So there is no optimization on the quantum part, no parameter or optimization either. So this is the figure to see it. And so the first thing is we need to figure out how we put the information into the quantum system and how we extract. And to do that, the extract is a measurement. Measurement needs to be simple, so we are just doing computational basis measurement. Then we don't touch quantum part, so that is make it much, much simpler to do this. So only input layer, how do we do encoding is a problem dependent. So here is a graph to computation to show when we're waiting time, the quantum computer think, and eventually quantum computer can produce the real sort of accurate answer. So this is the time we need, and then this is how it quantum computer solve a problem? Well, this is a simple, okay. But then, so maybe make it a little bit more complicated. So this is MNIST data. It's usually used for simple problem, simple test. And but this one now, we are thinking about only 12 qubits to solve 0 to 9, 10 digit numbers, 100 numbers. So it's much, much smaller than usually it's considered. And we use the classical processing using PCA and put that information into the only 11, here is only 11 qubits. Then we can see the testing accuracy is over 97%. So even just only 11 qubits can do this kind of thing. That's probably, it's a simple problem, you might think, but it can be exponential resource saving for the computation. And also, training is very, very fast because that we have only one layer classical neural network to train, so that the training is very fast. That is another thing. To see that what's going on inside of the black box, quantum black box, we have looked at the network property inside of it using that weight distribution. So here is a matrix of the unitary process, and we turn that into weight distribution. So this time is a weighted network we used. Then we can see that usually for the randomness, we use random unitary to be more complex, but actually what we see is our DTC model has a longer tail than our random matrix. And if we sort of follow this trend, then we used quasi-random unitary, and sort of it will give us a longer tail. And we can see if the tail is longer, and then so its color is, darker color is more accurate, so the testing accuracy is higher with darker color. So if you change the tail to be longer, and then we can get higher accuracy. So there are some correspondence between this. In this problem, I'm not saying this is true in general, we haven't proven it, but in this case, we can say this kind of trend. And if we have sort of changing it in a more physical way to do this is to add a disorder to DTC, discretized time crystal, then we can actually see naturally tail gets longer, and then accuracy in testing gets higher. So we can exploit this kind of natural system to this kind of computation. So quantum component is just sitting in the sort of classical computational environment and just providing the large network structure. And of course, the input and output is something we need to design, but this sort of opens up the many ways to use these kind of things. So it is a fast optimization and non-programming for the quantum part is needed. And sort of exponential resource, computational resource advantage is given, and we don't need programming. And if you want to run different tasks, you don't need any reprogramming in the quantum part. So this kind of thing can be a component to put into the classical environment. And also it is robust against noise because we are reducing information to get answer for this kind of problem. It is quite useful, and it can be done with much simpler systems as well. So even implementation can be easier. That's all for me today. Thank you very much.